Welcome to the class. So this is lecture 14 of our structure analysis course. So in this course we'll discuss about the internal loading at a specific point in a structure. So in the last few lectures we have discussed when we apply external load into the structure internal force is generated inside the structure. So what are the internal forces? We have discussed. So V means shear force, M means moment, N means normal stress. So all these forces are actually generated inside the structure. So the torsion and all also is the internal force. So upon application of external force, then only internal force is developed inside the structure. So this force in normal case, these forces are not visible. But when we take any section or if we take any cut into a body, then only these forces are visible. So in this lecture, we'll discuss how to determine the values of moment, shear force at different section of a structure. So let's first make our sign convention. So we'll use this sign convention for and throughout this course. So you can consider the opposite sign convention as well, but whatever the sign convention you have to assume that should be consistent throughout the solving the problem. So so this is our sign convention. So if you take a right side, if you take a section, so left side of the section, the downward force will call it positive. Similarly, anti-clockwise moment will be positive in the left side of the section. Whereas right side of the section, you will have upward force as a positive, upward shear force as a positive, clockwise moment as a positive, and similarly outward direction of normal force, we call it is a positive. So just to remember these things, we can just divide it into three different parts. So for example, if this is a body, and if you apply a pulling force into the body, then we'll call it this is a positive direction. So if the tension in a body, just for the remembering purpose, tension in a body, we call it positive. Similarly, if you apply a shear force and that shear force tries to rotate the block into a clockwise direction, then that type of loading direction we call it positive. So in our assumption we'll consider it as a positive. Similarly, which one is positive moment? So if a moment is applied to a body and the body is convex upside, so this is the direction. So that maybe it takes a bowel shape where water can be raised, so that shape we call it positive. So just this is sign convention. Just remember, if a body is in tension condition, then we'll call it is a positive. Similarly, if because of the shear force, if body tries to rotate it, then we'll call it is a positive shear force. Similarly, if a moment is acting on a body such that body is concave upside, then we'll call it is a positive moment. And the reverse case of this case will be the negative sign convention. So let's see what are the procedure for the analysis. So before analysis, first we have to compute is the support reaction, as we have discussed in the earlier sessions. So you will have a structure, maybe you have a structure of in this shape. So maybe, sorry, I'll just draw a simply supported beam. Simply supported beam means one hand will be hinge and another hand will be roller. So our first maybe some arbitrary loading is acting on a body. So our first job will be to calculate the what is the support reaction. The support reaction, if you draw, so you have the support reaction, this one vertically upward, here also it is acting vertically upward. So these two are support reactions. So our first job will be whatever beam will be given to us. Our first job will be to calculate what is the support reaction for this both the cases. So that is, if you see, that is the first step. Step will be support reaction. So before the member is cut, so before taking any cut of the member, we have to calculate the support reaction. It is necessary to determine the member's support reaction so that the equilibrium equation can be equal. So using equilibrium equation, basically you have to compute the support reaction. Similarly, if the member is a part or a pin connected structure, the pin reaction can be determined using the method of section. So if the structure is a truss member, then using method of section, you have to compute first the support reactions. So after you compute the support reaction, our next step will be to draw the free body diagram. So free body diagram means we'll take a section somewhere, the interest where we are to find it out. The internal forces there. So we'll draw the free body diagram and then keep all the distributed loading, couples, everything, whatever external loads are acting, that we have to draw it in. We have to keep it in exact location. Then we have to pass the imaginary line to make a cross section of the body. So after we draw the free body diagrams, our last step will be to use the equation of equilibrium to calculate the internal forces. Internal forces means moment, shear force B, and then N is the normal force. So all these are the basically internal forces we have to compute using the equilibrium of equation. So what are the equilibrium of equation? As we discussed in the earlier classes, we have the three equilibrium of equation: summation of all horizontal forces, summation of all horizontal forces equal to 0. Similarly, summation of all the vertical forces equal to 0, and summation of all moment about any axis should be equal to 0. So these three, using these three equations, equilibrium of equations, basically we have to compute the moment, normal force, and the shear force for any particular location. So now let's solve an example how exactly we calculate the internal forces. So here is a question. So given, so you can see this is a something like petrol pump's figure is given. So the roof, this is a roof, and this roof is resting on these beams. So these beams are again resting on this girder, plate girder. So this is a plate girder and this is the slab. So this slab is resting. Through this point, loads are transferred to this main beam girder. So what is the question? Question is the building roof as shown in the figure. So this is a figure, has a weight of 1 kilonewton per meter square. So the load, whatever load is coming from this slab is given as 1 point. So this whatever load is coming 1.8 kilonewton per meter square. So that much is the UDL coming. So that is given in the question, and is supported on a 8-meter long simply supported beam. So you can see this entire span, this span length is given to you. This is 8 meter. 8 meter span length is given to you. Now the beam that has spaced 1 meter. So this each beam is actually spaced. So this beam is actually 1 meter spaced apart. So each beam below as shown in figure, so it transmits the load to the girder. So each beam will transport the load to this girder. Okay, determine the internal shear force and the bending moment in the front girder at point C shown in the figure. Neglect the weight of the member. So this is the original beam. So what we do is we idealize the original beam into our analytical model. So now see, we convert its original figure into this analytical model. So in that analytical model, if you see, everything is same. Like total span length is given 8 meters. So this is total span length is 8 meters, and each beam. So if these small girders are actually 1 meter apart. So this from 1 meter. So concentrated loads are acting. So how much load is acting? That we have to compute. So this is our original beam, and also the load is given. So each concentrated load's magnitude is given 7.2 kilonewton. So each point 7.2 kilonewton load is acting. So you are asked to find out at this point C, which is actually 1.2 meter from this support. So this is 1.2 meter. At this point, we have to find it out the internal forces, basically bending moment and shear force at the point C. We have to compute. So that is the question. So now how to solve this? Our first job will be to calculate the support reaction. So how much will be the support reaction? So what we'll do, we'll just concentrate using the concentrated load. It is given 1.8 kilonewton per meter. So how much will be the support reaction in these two supports? So how to calculate? So we'll use summation of all vertical forces equal to 0. So what is the summation of all vertical force? So vertical force, if you consider this is A and this is B support. So RA plus RB equal to how much? Total load. So RM plus RB is acting upward, and what is the total load? Acting downward. So 1.8 kilonewton per meter is acting. So total, how much is the length? So total length is 7 meters center to center plus 0.5 this side, 0.5 this side. So total 8. So 8 into 1.8, that much kilonewton is acting. So if you multiply it, you will get. So if you multiply it, you will get 14.4 kilonewton. So Ra plus Rb is equal to 14.4 kilonewton. So this structure is actually a symmetric structure. So half of the load will come to A, half of the load will come to B. So that's why, so this by 2, so Ra will be 7.2. Similarly, Rb also will be 7.2. So that's what is we computed here, 7.2, 7.2, Ra and Rb. So that is our first step. First step is to calculate the support reaction. If you see in the last slide we have discussed, there are three steps to solve the problem. First one is to calculate support reaction. Next one is draw the free body diagram, and last one is apply the equation of equilibrium. So we have used our first method, first step, that is this support reaction we have computed, and each support has 7.2 kilonewton, 7.2 kilonewton. Our first job is over. So whatever I have explained, same thing is actually written here. Anyway, so next is we have to draw the free body diagram. So this is the free body diagram shown. So what is our question? Question asks to calculate the shear force and bending moment diagram at point C. So at point C, so let's assume the shear force acting is Vc and moment is Mc. That we have to compute this to value. So this is our free body diagram where we show the total load, how much is acting, and total how much load is. So this is original, just we have taken a cross section, right? So free body diagram is shown. So now 7.2 is reaction. So now this is the main girder. So each girder will have experience now 7.2 kilonewton force downward. So now if we draw free body diagram, so this is the free body diagram. So total how much will be the reaction in the girder? So reaction in the girder will be total 7.2 kilonewton. Kilonewton is acting in per meter width. So this distance is also 1 meter. So 1 meter into total center to center distance is total 11 number of loads are acting. So if you count here in the previous diagram, so total 11 concentrated load is acting, and each load has 7.2 kilonewton. So that will be the total load divided by 2. Half will transfer to one support, half will transfer to another support. That's why it is 2. And then at the corner, so corner you will have half, so 7.2, and it is in corner it will be half, 3.6. So the two sides we have 3.6 into 3.6. So total half again it will come to one support, another half will come to next support. So total each support will have 43.2 kilonewton. So now we will apply the equilibrium of equation to calculate the what is the moment and the shear force at point C. So apply first summation of all the vertical forces equal to 0. So what are the vertical forces now? So 43.2 is acting upward. So this is a reaction, 43.2 acting upward. And what is the downward force? Downward force is 3.2 kilonewton acting downward. So that's why it is negative 3.2, and 7.2 downward, 7.2 downward. So that's why it is 2 into 7.2 downward. And VC is the shear force that is also acting downward, right? So that is the VC into the minus VC. So from this equation you can easily compute what is the value of VC. Now similarly, to calculate the moment at C, what we have to do is, so our this is anti-clockwise moment we considered as a, so if you see the sign convention, anti-clockwise we consider it as a positive. So this MC is also anti-clockwise acting in this direction. So that's why it is positive MC plus 7.2. This 7.2 is acting at a distance of 1.2 meter distance. So that is 7.2. Sorry. So total distance will be 7.2. So 7.2. This 7. Let me just use high laser pointer. So yeah, so from here in this point we are calculating the moment. So MC is acting as a anti-clockwise. Anti-clockwise means positive, that's why it is positive sign. And what is the moment? So this is first force is acting 7.2 kilonewton, and how much distance from C? So this is 0.4 meter. So that's why 7.2 into 0.4, again, which is anti-clockwise direction. That's why it is positive. Now next force will come for this 7.2. This 7.2 is acting at a distance of 1 plus 0.4, 1.4 meter. So that's why 7.2 into 1.4, again the direction is anti-clockwise, so it is positive. Now plus 3.6. This 3.6 is acting how much distance, how far it is from C? It will be 1 plus 1, 2 meter, plus zero point 0.4, so 2.4. So this is 3.6 into 2.4, which is also positive because it is an anti-clockwise moment. And now last moment will come because of 4.3. This 4.3 basically clockwise moment at C. So 4.3 distance is 1.2. So 4.43.2 into 1.2. So from this equation again, now we can compute what is the value of MC. So like that, we can actually calculate at any point what is the shear force and the bending moment in a structure. So our first step will be to find out the support reaction. So that's what we have just calculated, support reaction. So our next job will be to draw the free body diagram. So this is a free body diagram we have drawn. And the last step is apply the equilibrium of equation, that is summation of all the horizontal forces equal to 0, summation of all vertical forces equal to 0, and summation of all the moment about any particular point should be equal to 0. So using these three equations, we can easily compute all the internal forces. Internal forces means shear force and the bending moment. So at any location we can compute. So here in this problem, we are asked to find out what is the shear force and bending moment diagram value for the point C. So similarly, any point actually we can compute what is the internal forces. So today's lecture we have discussed how to actually find out internal forces at the particular point in a structure. So in the next lecture we'll elaborate and we'll find it out how to draw the bending moment and the shear force diagram. Thank you.